Good morning, dear students. In a previous lecture, we have gone through the detailed description of various crystal systems, Bravais lattices, space lattice, unit cell. Now, the next concept is why there is absence of 5-fold, 7-fold, 8-fold or higher fold axis of rotation in crystals. Now, in the 7 crystal systems we have discussed so far, we have not studied any crystal system in which there is 5-fold, 7-fold, 8-fold or higher fold rotation axis is present. Now this is due to the reason when we are building up a crystal lattice by repetition of unit cells in 3 dimension, there is condition is required the faces of each unit cell must touch the faces of adjacent unit cells without leaving any vacant spaces in between them. So, close packing of unit cell is much required when we are building up a space lattice by joining the unit cells. In case of 5-fold, 7-fold symmetry axis, the close packing of unit cells is not possible. As we can see in the figure in the next slide, where we have arranged the objects having 6-fold axis and 5-fold axis of symmetry for comparison. As we can see here, two-dimensional arrangement of hexagons and pentagons. We see that in case of hexagon, there is close packing of the unit cells and we are not having any gap in between them. There is no vacant space here. In case of pentagons, where there is 5-fold axis of rotation, we are having a gap between the unit cells when we are joining them to form the space lattice. Now why this gap is appearing here? We can see here the angle is 120 degree for each hexagon. When we are joining them together, we are seeing here the total angle of 360 is obtained by joining the 3 hexagons together. In case of pentagons, when we are joining them, each one having angle 108 degree, on joining them total 360 degree angle is not obtained. That's why there is gap in between them. So 5-fold, 7-fold axis of rotation will not be possible in case of crystals. The reason being the close packing of unit cells is not possible when we are joining them to form a space lattice. Now the next concept is isomorphism and polymorphism. In case of different substances having crystals which are similar in shape, we call that phenomena as isomorphism. When we are having the crystals of different substances which are having similar shape or morphology, we call them isomorphous compounds, and this phenomena is known as isomorphism. And these isomorphic crystals will belong to the same crystal system. That's why they are having similar shape. Now, for an example, we can see here sodium phosphate and sodium arsenate. These two are having similar chemical composition and are having same crystal shape or crystalline form. So such type of crystalline substances which are having similar chemical composition and they are possessing the same crystal shape will be known as isomorphic compounds. So how we can define this? When crystals of different substances having similar chemical composition existing in same crystalline form, the property will be known as isomorphism. Now in opposite to it, what we can see in case of many substances, there is more than one crystalline form is possible. For example, in case of carbon, it exists in 2 crystalline forms, diamond and graphite. In case of sulfur, it also exists in 2 crystalline forms, sulfur rhombic and sulfur monoclinic. So such type of substances which can exist in more than one crystalline form are known as polymorphic compound and showing polymorphism. Now when this polymorphism is exhibited by the elements, we call it as allotropy. And these different crystalline forms will be formed under different conditions of temperature and pressure. These different conditions will lead to different crystalline forms of the same substance. Now, the temperature at which this one crystalline form will change into another crystalline form will be known as transition temperature. So how we can summarize this? In case of isomorphism, it is describing the presence of same morphology in different substances. Whereas in case of polymorphism, it is describing the presence of different morphology of the same substance. So when different substances are showing same morphology, we call it as isomorphism. When same substance is showing different morphologies, we call it as polymorphism. Now how we can calculate the theoretical density of a crystal? For this we can use the relation derived here. The density is equal to Nm divided by Avogadro number into volume, where N is the number of atom, molecules or ions present per unit cell. M is the molecular mass. V is the volume of the unit cell. And Na is here the Avogadro number. So how this is equal to the density of the unit cell? Total mass of the unit cell divided by total volume of the unit cell. Now total mass of the unit cell will be obtained from the total number of atoms present in the unit cell, and that is equal to N here. Now M by Na, that is equal to mass of a single atom, which is ratio of molecular mass divided by Avogadro number, that is giving us mass of a single atom, and total n number of atoms are present in the unit cell. So total mass of the unit cell is equal to N into M by Na. Now dividing this total mass of the unit cell divided by volume of the unit cell, we are getting here the density of the unit cell. So theoretical density of a crystal can be calculated by using this relation. Now what about the space groups? Till now we have discussed about crystal systems, Bravais lattices, point groups. And we very well know point groups are what? These are the 32 possible ways of arranging elements of symmetry around a single selected point. Now when these symmetry operations, they are combined with two additional translational symmetry elements, which we know as screw axis and glide plane, then they will generate total 230 different arrangements, and these arrangements will be known as space groups. So when we are combining two additional translational symmetry elements to these point groups, we are getting total 230 different arrangements of elements of symmetry, which are known as space groups. So space groups can be defined as the 230 different arrangements of elements of symmetry about a lattice point in the crystal. Now any crystal will belong to one of these space groups. Whatever crystal it is of any substance, that will belong to one of these space groups. How these space groups are distributed among 7 crystal systems, we can see here. In case of cubic system, 36 space groups. In case of tetragonal system, we are having 68 space groups. Similarly, various other systems are here, and we are getting here different number of space groups corresponding to different crystal systems. So what we have discussed till now, there are total 7 crystal systems, there are total 14 Bravais lattices, there are total 32 point groups, and there are total 230 space groups corresponding to different arrangements of element of symmetry about a lattice point in the crystal. So this is all about the detailed description on the external geometry shape, various crystal systems, phase groups, point groups corresponding to a crystal. In the next lecture, we will continue with the study of internal structure of crystals by using X-ray diffraction. Thank you.